I'm an art student. Our chemical journey begins with a small molecule called ozone. Ozone, or O3, is a gas molecule made up of 3 oxygen atoms. It's most often found in 2 places near the Earth's surface and in the stratosphere. Ozone is formed in the stratosphere when photons are energetic enough to separate oxygen molecules into atomic oxygen. These atomic oxygens then rearrange themselves into ozone molecules. We've all heard about ozone before, usually in relation to pollution. Ozone gets dangerous when humans have close contact with it because high ozone exposure increases the risk of respiratory disease, acute asthma, and premature death in humans, which is not very healthy. However, we still need ozone to survive, just not around our lungs. See, there are massive amounts of ozone located in the stratosphere called the ozone layer. Due to ozone's absorption of ultraviolet radiation, the ozone layer functions to protect humans against overexposure to the sun's UV rays. But how does it do that? I'm so glad you asked, classmate or random pedestrian. First things first.
The sun is a deadly laser.
But ozone fixes it.
Okay. Not anymore, there's a blanket.
The sun emits radiation. Yeah, probably figured. That's pretty good. Most people, yeah. Radiation is defined as electromagnetic energy released in the form of a particle or wave. This unit of energy is called a photon, or a particle of light. And these photons function differently than other particles. For example, photons don't have mass. As mentioned before, photons function in waves. The faster these waves move, the shorter the wavelength becomes, and the more energy they have. If a photon's wavelength is shorter than the violet side of the light spectrum, then it is ultraviolet or UV radiation. An ultraviolet wavelength is near or smaller than the diameter of an atom. This allows UV radiation to alter or break bonds in different molecules. However, certain bonds require more energy and therefore a shorter wavelength to break. Our atmosphere is about 21% oxygen. It takes a photon wavelength of 242 nanometers or shorter from the sun's UV light to break an oxygen bond. However, for ozone, it takes a wavelength of 320 nanometers or shorter to break an ozone bond. This might first seem like a problem, seeing as ozone is less resilient to ultraviolet light than oxygen. However, the ozone would actually be absorbing that radiation to break apart, ultimately decreasing the amount of UV rays that hit the Earth's surface. Not only that, but after breaking, those ozone molecules would then branch out into oxygen, which can still be broken down afterwards. This process is how the ozone layer acts as vital protection, which of course means, if you're studying environmental chemistry, that we've just completely ruined that by now. Unfortunately, ozone holes exist. An ozone hole is considered to be an area of the atmosphere that has less than 220 Dodson units of ozone. 1 Dodson unit is the equivalent of 2.69 times 10 to the 16th molecules of ozone per square centimeter. Over the last few decades, ozone holes have been growing at a rapid rate, especially around the South Pole. It does not look good. Ozone holes are most often caused by human activities, pollutants, and gases, most notably chlorofluorocarbons. Chlorofluorocarbons. Say it with me. Chlorofluorocarbons. I don't actually know if you said it with me, so good job, or too bad, or... Anyway, chlorofluorocarbons, which are not as fun as they are to say, are also called CFCs if you're boring. These are synthesized compounds composed of chlorine, fluorine, and carbon. Hence, chlorofluorocarbon. The brand name is also known as Freon. CFCs were most often used as refrigerants, aerosols, and repellents through the 1930s to 1960s. The two most common chlorofluorocarbons. The 2 most common CFCs are trichlorofluoromethane, also known as CFC11, and Dichlorodifluoromethane, also called CFC12. I had to record that so many times to get it right. This is what CFC12 looks like. See how even it is? CFCs have chemical structures that are perfectly balanced. The base carbon is connected to the chlorine and fluorine atoms without any extra valence electrons. Chlorofluorocarbons are so stable that they're non-flammable, non-toxic, non-reactive, and virtually indestructible. This allows them to float into the stratosphere without burning up in the troposphere. They're also really cheap to produce, which made people want to make them more, even though they don't burn up in the troposphere. When they're exposed to the heightened radiation in the upper atmosphere, the chlorine breaks off from the base carbon into a free radical. Free radicals are particles with unpaired valence electrons. In order to fulfill their pair, they become highly reactive. So, the chlorine radical would try to react with the ozone. When that chlorine-free radical meets the ozone molecule, it creates chlorine monoxide and oxygen. As you can see, chlorine monoxide is also a free radical. Afterwards, when that chlorine monoxide meets atomic oxygen, they react with one another by creating oxygen and another chlorine-free radical. This chlorine is never entirely destroyed. It becomes a catalyst that is constantly creating oxygen while destroying ozone. So why is this important? What does ozone actually protect us from? Well, as mentioned before, without the ozone layer, excess ultraviolet radiation bleeds onto the Earth's surface where we live. While yes, humans do need certain amounts of UV radiation to survive, excess UV light on the skin causes a series of events to occur in the body. Step 1, UV energy is absorbed into our skin cells. Step 2, H2O molecules, water molecules, dissociate into free radicals and destroy cells. Step 3, broken DNA cells can mutate and cause skin cancer. Melanoma skin cancer is the third most common cancer for people ages 15 to 39. So what do we do about it? How do we fix this massive, dangerous problem in our air? Well, for one, we can start with legislation. And we already have. The Montreal Protocol is an international environmental conservation treaty that was signed in 1987 by 198 countries. It asks to phase out the use of chemicals responsible for depleting the ozone layer, primarily chlorofluorocarbons. It is actually considered to be one of the most successful environmental agreements in history. In 2016, scientists discovered the ozone layer's first signs of natural healing after years of exposures to depleting chemicals. Unfortunately, there has been an increase in CFC emissions since then. Now, scientists originally considered the reasonings for these spikes to be because of illegal production. In 2013, there was a discovery of illegal CFC production from a source in eastern China. However, it is more likely that these CFC emissions are rooted in things called CFC banks. CFC banks occur when old industrial equipments made before the Montreal Protocol break down and release CFCs into the atmosphere. These old products were originally assumed to have very little impact on the environment, but things like insulation foam, cooling systems, old refrigerators continue to deplete the atmosphere. A team of scientists found that the amount of CFC11 and CFC12 in these banks are around 2.1 million metric tons. That is the equivalent of 9 billion metric tons of carbon dioxide of environmental harm. That amount of chlorofluorocarbons would stall the recovery of the ozone layer by 6 years. But here's where human error comes into play. These CFC banks were originally discussed to be destroyed in 2000. If that had happened, it would have stopped the equivalent of 25 billion metric tons of carbon dioxide of environmental harm. But we didn't do anything about it. Along with legislation, another practical question remains. How are we going to replace chlorofluorocarbons? Well, as of right now, the current replacement is not particularly viable. The most common replacement for chlorofluorocarbons are hydrochlorofluorocarbons, also called HCFCs. As you can see here, hydrochlorofluorocarbons are chemically similar to chlorofluorocarbons. The only difference is that one of the CFC's chlorine atoms is replaced by a hydrogen atom. However, this isn't really a fix-all solution. HCFCs only have one less chlorine atom than CFCs, but that other chlorine atom is still there. While HCFCs can burn up more easily in the lower atmospheres, those that do reach the stratosphere can still react create those chlorine-free radicals and continue to deplete the ozone layer. The only difference is that they would be doing so half as fast. There is still a lot to be desired regarding ozone depletion, and much more to be desired about how we've been handling ozone depletion in the last 2 decades. We have been able to rectify all the damage caused by chlorofluorocarbons, and there's still yet to find a similar, cleaner replacement. But the ozone layer is healing. It's just taking a drastic amount of time.